Hi, welcome back to Econ 3020. It's after spring break. COVID-19 has come to America, and SUU is shut down for the rest of the semester, and we'll be doing this online. You'll be doing more than one kind of video with narration in this class. This one here is to go over kind of review stuff from the handbook that we did immediately before break. So this is kind of what I would have done in class on the first day for 5 or 10 minutes just to kind of refresh your memory. So I'm going to be using this software that records my screen, and I can put the handbook on the screen like so. My intention is not that you really be able to read this necessarily very well. I think it should be readable. But my intention is more that you have the handbook with you so that you can see what I'm referring to or usefully talk about what I'm referring to. So anyways, where we are in the time series is we started out with case 1, which is the plain vanilla case that lots of people do with time series analysis, where they just regress the data on some sequence of integers like dates, or in our case, years. I showed in class that this doesn't work with macroeconomic time series, and the same thing follows over for financial time series as well. It appears to fit very well, but then you look a little more deeply and it doesn't fit very well. So it has a high R squared, making you think that it fits well, but that's because it's compared to a case that's kind of meaningless in time series, as I showed in class. When you actually look at the standard errors, they're quite large. And when you look at how it fits versus business cycles, it does a terrible job. So that first instinct of people to do the easiest thing is dead wrong in doing macroeconomics and financial time series. This is unfortunate because there's lots of software that will fit a time trend for you automatically, including Excel. And nobody tells you that this is a bad thing. So after going through after going through case 1 here, and I'm going to go out several pages now. So I am now on, that's more than I thought. Okay, I'm on page 213 where we talk about case 2. In case 2, what I do is add a lag dependent variable to the model. So we have a deterministic trend in there, that just means a sequence of integers, and a lagged dependent variable. Okay, when we estimate that model, and I'll advance here to page 214, and if you hear rustling of my pages, okay, you know what I'm doing. Okay, and I'm going to go down a page just to check. Okay, so this one does not have a page number in this visual, which is kind of weird. I'm showing it as 214 in the file on your screen, but in the copy of the book I have in front of me, it's 212. So I'm thinking 214 is what's correct for what you guys have in your hand. My edition may not be quite as up to date as yours. Okay, so anyways, if my page numbers are off by 2, you know why. I'll try and fix that after this video. So when we did this regression, we found down here that what happened is the deterministic trend variable became insignificant when we included the lag, and the lag was highly significant. So that tells us that we probably ought to drop out the deterministic trend variable. Okay. Now here's the thing. In case 1, we're fitting the trend with the deterministic trend. In case 2, we're fitting the trend with that deterministic trend term. Now for case 3, I'm talking about getting rid of it so we won't be fitting the trend at all. So advancing forward, to case 3, which in this version is on page 221. The one I have in front of me, it's 219. Okay, we get this estimate down here. Now, a point that I did not make well in class before break, and I probably should have, is that this does not fit the trend at all anymore because we've dropped out the deterministic trend, and it's not yet case 4 where we fit the trend stochastically. Instead, what this is saying is we're allowing the coefficient to be free here, and it's very close to 1, but it's not exactly equal to 1. As I discussed in class the week before break, this means that this model is saying that there's no trend at all in the data, but instead what we have is extremely long memory, okay, that shocks last for a really, really, really long time. So basically it's saying the last 300 years is kind of a bump in human existence, okay? So if you go back to the first week of semester where I drew that hockey stick diagram that basically was flat and then went straight up as a measure of well-being, this model is saying that that straight up part is the front end of a huge hump that could last, I don't know, hundreds or thousands of years, okay? Which seems pretty weird, but of course, I suppose it's possible, okay? My main reason for doing this is not to talk about case 3 more, but to contrast this with case 4. So case 4 is where we go ahead and we look at this coefficient and we look at this standard error here and we calculate this 95% confidence interval over here, okay? And we say that that includes the value of 1, okay? I'm going to be smart here and try something. I can actually highlight that. Right. I can't highlight it because it's an image. It won't work. Okay. Should know my own document better, but I don't. Okay, so anyways, what this is telling us is that the coefficient is indistinguishable from 1. That means in econometrics terms that you probably ought to think about restricting it to be exactly 1. Now, as I mentioned before, part of the problem with Excel is that it can't actually do a regression where a variable is restricted to 1. Okay, but Stata can. Most other programs can as well. Okay, and so you actually can, okay, see an estimate of this from Stata on page, fishing through here, I probably should have marked this. On page 382. Okay, so it is a doable thing. Okay, just not in Excel. Now, part of the reason that I want to use Excel for this class is everybody's got it on their desktop, and you may not have Stata going forward. Okay, so suffice to say, we can't actually estimate case 4. We're going to fake it in Excel. Getting back here to the confidence intervals, okay, there is actually a huge and very complex literature and time series about how to estimate these things, okay? But there are some results that are probably more obscure than they ought to be. That say from a Bayesian perspective, you can actually trust this confidence interval here. So we're getting a fairly tight estimate around 1. I mean, between 0.98 and 1.02. That's fairly tight in on the value of 1. Okay, so it makes sense for us to restrict it to be 1. So if I go forward a couple pages from here, okay, page 222 has the math that we did in class on the board that discusses what happens if we continue to do a repeated substitution of the model in case 3. Okay, so what we do in equation 76, okay, is start out with the regression that we actually ran in case 3. In equation 77, I bump it back by 1 year or 1 period. In equation 78, I substitute in the right-hand side of 77 here, okay, in, oops, here in equation 76, okay? So I'm taking advantage of the fact that the yt minus 1 shows up both here and here, okay, to make that substitution. And we get this thing down here, and in equation 80, I group things together as I did in class, okay? In equation 81, I bump 77 back by another period and do the substitution again in equation 82 and gather terms in equation 83. Okay, and what this points out to us is this pattern that we're going to have, that the intercepts are being weighted by the betas. Okay, the y is being pushed back and weighted by the betas, and the errors or residuals are being weighted by the betas. Okay, now the cool thing about this, okay, is if beta is less than 1, it tells us what's going to happen with all these. Since this is raising beta to a power, the effects of the intercept and the regression are going to fade out going into the past. Okay? And the effects of the residuals are going to fade out going back into the past. But the effect of that middle term there is going to get smaller and smaller and smaller. Since beta is between 0 and 1, we raise it to larger and larger powers, and the result is that limit is that's going to 0. And we can see this on the next page. Okay, actually 2 pages out. Okay, we get this equation here. So this left-hand side here is equation 76 from a couple pages back, and the right-hand side is the limit of this thing that we get if we re-express these things. Now this is pretty cool because one, the first term here, whoops, on the left is just a constant, okay, and this second term here is just the sequence of estimated residuals getting weighted so that the residuals, that the shocks that hit the economy further in the past, are less important. Okay. Now, some terminology. Going back 2 pages, we call a model like case 3 an AR1 model. I've got that up here. AR1 means it has 1 lag, and AR is short for autoregressive, and that's the case where the beta is between -1 and 1, okay, but strictly less than 1, okay. Going forward 2 pages, okay, this expression here is called a moving average, okay, and the term in parentheses would go infinitely far back, so it would actually be an infinite order moving average, an MA infinity here, okay. Turns out any autoregressive model can be converted into a moving average model, and any moving average model can be converted into an autoregressive model. Okay, it's a very cool resultant time series that allows us to figure out how things move through time. The advantage of the AR model in our case is it's easy to regress in Excel, and it has a very easy to interpret regression because it's only got one variable on the right hand side. The advantage of the moving average model is that it shows us how today's data is composed of weighted additions of shocks that hit the economy in the past, fading out as we go further and further back. Okay. Now, going forward to page 226, okay, we get this idea of transitory shocks. Okay, we We know what shocks are. Okay, those are the things we estimate from the residuals of the regression. Those are the things that are buffeting the economy. And transitory means that their effects eventually fade out. So going back 2 pages here, okay, this result right here and the parenthesized term on the right hand side is saying that if the betas are larger or are less than 1, excuse me, and we're raising them to larger and larger powers, we're putting a weight on those residuals, on those shocks, that is smaller and smaller and smaller the further we go back in the past. So what we experience today, or what we measure today, has got a little bit of every shock that ever hit the economy in it, but very distant shocks in the past are not very important. Okay? The thing is, in the case where beta is actually equal to 1, those shocks never fade out. Okay? So if beta is less than 1, the shocks fade out, and the word we use for that is transitory. If beta is equal to 1, the shocks never fade out, and the word for that is permanent. So going forward 2 pages, we have a section on transitory shocks, and then we have a section following that on permanent shocks. Okay? So we really don't ever know whether the coefficient is insignificantly different from 1. We get estimates that it's insignificantly different from 1, but we never know that in truth. So we're making kind of a leap in faith here that it is 1. Okay? In the case where it is 1, we do have a stochastic trend in the model. Okay? That's picked up from the intercept term, which in these models we call drift. And that drift term, okay, is picking up the trend, okay, when combined with that autoregressive coefficient that's equal to 1. This is so special, we call this model a unit root model, okay? Some people will also call it an integrated model, so it's an I1 model, which I'm highlighting right now. And in finance or investments, these are often called a random walk or a random walk with drift. Okay, they all mean pretty much the exact same thing. Okay, what was happening there is people were coming at these from different directions, giving them different terminology, and it took many decades of work to actually show that they were all getting to the exact same point. Okay. So anyways, case 4 is the one that cannot be estimated by Excel, but we can fake it. And the way that we actually do that is by going to the next page here, and this is new math here. Okay, but if we impose the restriction that the coefficient is equal to 1 instead of estimating it, okay, then we can actually just shift it over to the left-hand side over here, okay, and then just say, well, that's just the difference in y down in equation 88. So since we're dealing with log data, we now have difference logs on the left-hand side, which is an approximate growth rate. And on the right-hand side, we're saying that the approximate growth rate is equal to a constant plus an error. And we can estimate that constant down here. Okay, right in here, I get an estimate of that of 0.0338. Okay, which is roughly 3.4% per year. And then everything else is a residual. Okay, so that's where we are with case 4. Okay, I'm going to switch to another video now. Okay, I just wanted to make sure that we note that this page goes on, and here is our model for case 4 right here. In class, where we were using a sample that was slightly different, we got a slightly different result. Okay, I'll see you guys in the next video. Bye.